All right. Hello, everyone. Happy second to last week of discussion. Y'all made it this far. We are on day 11 now. So we have one more next week, right before we get out for Thanksgiving. And then you have officially completed systems physiology discussion. So congratulations. This is a very hard class and be proud of yourself that you've made it this far. So anyways, today we are going over renal epithelial transport. This is kind of a tricky discussion worksheet as it involves some calculations. And it's not that the calculations are hard at all. They are pretty simple calculations. It's understanding the variables behind or inside of the calculations. So kind of how we're gonna go through today is we're gonna do a quick overview of just the renal system in general, some of the things that we need to know to solve, and then we will get into the discussion worksheet, work through those first two kind of word problems, and then move on to the calculations. So let me go ahead and share my screen and we will begin. Also, I will be kind of flipping back and forth between my iPad and my laptop, so be prepared for maybe some technical lags. Hopefully it goes smoothly, but we will see. All right, so again, discussion 11. So before we hop on in, I did want to make some quick announcements. So exam 4 scores were pretty low. The average for the online exam was a 63. The average for the in-person exam was a 71, bringing the overall average to a 67. So average was pretty low compared to the last 2 exams. So I'm assuming that most of you, or a good chunk of you, are probably going to want to review what you missed. And so if you want to do that, make sure you email one of the UGTAs. They are responsible for reviewing the exams. I do not have possession of the exams. They have the exams, I do not. So if your last name begins with A through L, email Marissa. If your last name begins with M through Z, email Matthew, as that's how they split them up. So if you want to review them, just shoot them an email. Y'all can schedule an appointment and go over them. Also, if you have any concerns about the last couple reading quizzes we have, or any reading quizzes in the past that something is bothering you about, email the UGTAs as well. They are responsible for creating the reading quizzes. They understand the rationale behind the answers and all of that. And they can go in and give credit if needed. They take care of exam reviews and reading quizzes, so please do not email me about that as my inbox gets overloaded. Shoot that to the UGTAs because they'll be able to quickly help you out. But yeah, again, next week is our last discussion. So I will see y'all then, right before Thanksgiving. And then look out for those course surveys that you're going to get. As someone who really wants to go into academia and be a professor, you don't understand how much we value that feedback. You know, most of the time people just go on to give feedback whenever they are mad. That's something that I did in undergrad. Was I never really gave positive feedback to the professors that were great, and I kind of gave negative feedback just to the ones that I think needed to hear it. So make sure that even if you don't have anything bad to say, go and leave a kind review because we read them all. And so, you know, whether you have suggestions on how we can change our teaching style, something you liked, something you didn't like, you know, it means a lot to us for y'all to complete those surveys. And it kind of gives us an idea on what we need to tweak, what y'all like. And, you know, it's just kind of like the one chance that we get feedback on how we're doing. So whether you have something bad to say or something nice to say, make sure you complete those because they are pretty important to us. All right, awesome. So now that I'm done with announcements, we're gonna hop on in. So look at this beautiful picture we have here. Oh, how complex our body is. So what we're looking at here is the nephron. So this is the nephron. It's quite complicated. There's a ton of these in the body. I wanna say like 1 million or 1 billion or something like that. There are a ton of these little guys. They are the functional unit of the kidneys. So we're going to hit this diagram pretty hard in lecture, but there are just some things that I want to point out that will kind of, you know, help us with working through today's discussion questions. So one thing that's important to note is that blood comes in through the afferent arteriole. So blood is what the nephron is filtering. We take substances out of the blood to create urine. So blood is carried in through the afferent arteriole into the glomerulus. You can think afferent arrive, efferent exit. So afferent is bringing the blood into the glomeruli, and the efferent arteriole is carrying it away, exiting. So what we see is that, of course, 100% of that blood enters into the glomeruli, and 80% of it's going to leave, leaving us with 20% that will enter the nephron. So about 20% of that blood that's filtered in the glomeruli is going to enter into the nephron. That is that first, step of filtration that we see here, filtration. So we have filtration, we have reabsorption, we have secretion and excretion. So those are those four main steps of, creating urine, filtering the blood, all of that. So we filter the blood in the glomeruli, we will reabsorb and secrete substances along the way, and then we will eventually excrete the newly formed urine out of the body. So whenever we're dealing with the glomeruli, this section right here, and dealing with the filtration portion, there is something called the filtration barrier. And it consists of three important layers that kind of serve as the filter. So first we have the capillary endothelium. And what we see is that the capillary endothelium serves as a size barrier because it has large pores that will let certain molecules in and out. However, the pores aren't, they're a pretty specific size because they're not large enough to let in molecules like blood cells, things like that, but they are large enough to let in, molecules of sodium, potassium, urea, chloride, things like that. So they kind of work as a size barrier. But again, they're going to make sure that those pores aren't large enough to let in like red blood cells or anything like that. Next, we have the basement membrane. So the basement membrane serves as an electrical barrier because it contains negatively charged plasma proteins. So it's only going to let in positive ions because like and dislike go together. Remember, like and like repel. If you have two negatively charged ions, they'll repel. So that negatively charged plasma protein barrier in the basement membrane will let positive ions in, but repel negative ions. So what we see is that we like to let in small, positively charged ions, molecules. And then lastly, we have one more size barrier, which is the Bowman's capsule epithelium, and it also has those pores that will serve as a size barrier. So you can see those here, those podocytes. But again, they're not going to let something in as large as like a white or red blood cell. They like those small, positively charged molecules. All right, great. So my animation's a little bit messed up on this. Sorry that some things are already filled in, but we'll work on through it. So what we're looking at now is the driving force of filtration. So we're looking at what actually causes blood to leave the glomeruli, enter into the Bowman's capsule, and be pushed into the nephron itself, all of those tubules. So what actually causes this? Well, we have three mechanisms. We have hydrostatic pressure, we have osmotic pressure due to osmolarity, and we have fluid pressure created by the Bowman's capsule. So what we're going to see overall is that this hydrostatic pressure, aka blood pressure, is going to be the main driving force. It is the strongest and most potent driving force for filtration. But these other two kind of act in opposition to that driving force. They kind of actually serve as a resistant force, and we'll look at why. So again, blood is brought in through that afferent arteriole, and as well as blood, so is water. Water is in blood, water plasma. So when water enters in through the glomeruli and into the Bowman's capsule, what we see is that the osmolarity will be altered. So we'll have an increased osmolarity inside of the glomeruli, which means we'll have a decreased osmolarity outside in the Bowman's capsule. We know that molecules in our body like to move from high to low. Therefore, we're kind of acting as a resistant force here, because whenever there's fluid outside of the glomerulus, it's exerting pressure onto the vessel walls. So it's kind of resisting that gradient. So that's one of those reasons how we move blood from the glomeruli into the Bowman's capsule. We also have just fluid outside in the Bowman's capsule. And what we see is that whenever there's fluid outside of the glomerulus, it will also exert pressure. Kind of similar to hydrostatic, except it's coming from the outside of the glomeruli. So it's kind of also serving as a resistant force. However, that hydrostatic pressure or that blood pressure is usually higher than both of these resisting forces. So it is truly the driving force of filtration. So the net filtration pressure, that is that driving force. Dr. Chang will go more in depth with this, so if my explanation was a little confusing, we haven't hit it in lecture yet. So don't worry too much about learning it here. I just wanted to give a quick overview. So back to this picture, there's one important variable, extremely important variable that we will be using today, and it is glomerular filtration rate. So this F right here, filtration, that is really, in big terms, the glomerular filtration rate. And something important to know is that it is completely influenced by the afferent arteriole. So glomerular filtration rate is looking at the total blood filtered in the kidneys per day. And the afferent arteriole is what regulates that process. So the afferent arteriole regulates, how much blood is going to be filtered into the kidneys per day. So let's kind of look at how. So there are two ways that the afferent arteriole regulates blood flow, or how much blood is going into the kidneys, the nephrons per day. And the first mechanism is the myogenic response. And this is the lesser mechanism of the two. The next one we look at is the main mechanism, but we also have this mechanism called the myogenic response. So what we see is that when we have an increase in blood pressure or an increase in blood flow, we have an increased glomerular filtration rate. And that would make sense. We're sending more blood to the kidneys, so the filtration rate is going to increase because we need to filter that extra blood that we're sending. We have our regular blood vessels, but once we increase that pressure, the afferent arteriole will detect that. It will detect that we're sending more blood through that, through those vessels, through the afferent arteriole at the capillary bed of the glomeruli. And what it will do is it will cause the vessels will stretch. So the vessels stretch whenever we increase blood pressure. And when they stretch, what we see is the opening of mechanogated calcium channels. And this causes an influx of calcium into the vessel walls. So once those vessels are stretched due to an increase in blood flow, we open these channels, these calcium channels, mechanogated calcium channels. Calcium flows into the cell. And when calcium flows into the cell, into the smooth muscle of the arteriole, more specifically, it will bind to that troponin and tropomyosin complex and remove the actin from the myosin, revealing those myosin binding sites so that cross-bridge cycle can occur. And what we see is contraction, aka vasoconstriction. Our vessels don't really contract, they either constrict or dilate. So when those calcium ions flow into the smooth muscle of the arteriole, the smooth muscle in the walls will cause the arteriole to vasoconstrict. When this occurs, we see an increase in resistance because we have a smaller tube now, which causes a decrease in blood flow and overall a decrease in our glomerular filtration rate. So, that is a negative feedback mechanism there. We increase glomerular filtration rate. That's not a homeostatic response. We don't want to have high blood pressure all the time. We don't want to be over filtering our blood. So our body will work through this mechanism here and use the myogenic response to decrease that glomerular filtration rate. So increase in blood pressure means increase in filtration rate, which means those vessels will stretch due to the increase in blood flow, which the myogenic response will detect that, open those mechanogated calcium channels. Calcium will flow into the cell, causing, or I keep saying the cell, sorry, into the smooth muscle cells of the arterial, causing them to constrict, vasoconstrict, which leads to an increase in resistance, decrease in blood flow, decrease in glomerular filtration rate. So, some of these go together. You don't need to know, that increase in resistance, decreased blood flow, which decreases that. If you know that there's a decrease in GFR, you would know that there's a decrease in blood flow and a decrease in blood pressure. Those all go together. So that's the first mechanism for regulating filtration or blood flow through the glomeruli. Let's look at the second one. Now we have tubuloglomerular feedback. Tubuloglomerular feedback. And this is kind of the more important and stronger way to regulate blood flow through the nephron. So what we see is it's another negative feedback mechanism, and it kind of works, a little bit similarly when we look at the overall process, but how it does so is different. So let's start working through it. So first, what we see is, of course, that increase in blood flow and that increase in glomerular filtration rate. We see that right here. Again, blood flow, blood volume, blood pressure all go along with GFR. So if we know we have an increase in GFR, we know we have an increase in blood pressure, we know we have an increase in blood volume, we know we have an increase in blood flow. So just associate those all together. So what we see is that increase in GFR is going to cause, an increase in blood flow through the nephron. We are, putting a lot more blood into the nephron due to that increased blood flow. And that increase in blood flow is going to move through the nephron. And what we see is that these specialized cells that surround the tubule are called the macula densa cells, and they are going to detect that increase in blood flow. So these macula densa cells surround this tubule, and they will detect this increase in blood flow. When they detect that increase in blood flow, they send a signal down to the granular cells, and the granular cells surround the afferent arterial. If I could zoom in, I could show you that they surround the afferent arterial and cause the afferent arterial to constrict. This constriction, vasoconstriction of the afferent arterial will increase resistance, decreasing blood flow and decreasing glomerular filtration rate. So the big thing here is, we increase blood flow, we increase glomerular filtration rate. This causes an increased flow through the nephron. The macula densa cells are going to sense that increase in blood flow. They surround the tubule. They will send a signal to the granular cells that surround the afferent arterial, causing that arterial to constrict, therefore increasing resistance, decreasing blood flow, and decreasing glomerular filtration rate. So, filtration, blood flow through the kidney is very complex. So make sure you're going through this a few times because, these are weird structures and weird processes. So make sure you understand this negative feedback loop and how we control blood flow through a kidney. All right, so now we're going to look at glucose handling. And this is telling us how the kidney is dealing with glucose. Are we going to reabsorb it? Are we going to filter it? Are we going to secrete it? What's the net process that's overall happening when we're dealing with glucose in the kidney? And this is important because, if we have glucose in our urine, that's a sign of diabetes. It could be a sign of other things as well. So, glucose filtration in the kidney is pretty important. So what we see, and I definitely recommend drawing this out with me, is we first have this line. And this line is showing us the filtration of glucose. So this is just kind of our control line, showing us how glucose is filtered. However, it doesn't go all the way to the top. It's not this linear progression that we see here. Instead, we hit a plateau. So we hit a plateau right here. This R is talking about the reabsorption of glucose. So what that tells us is that our kidneys can filter glucose, as much glucose as we put in, but we can only reabsorb a certain amount of glucose. So we can filter it and get it into the nephron, but we're not going to reabsorb it all. That's not good. So let's analyze the different sections of this graph. So this first section here is showing us, sorry, it should be the green line, showing us, the normal filtration of glucose. As long as we don't hit this plateau, we will filter as much glucose as we reabsorb. So when we're looking at this chart, we're adding glucose to our blood, our plasma, and we are reabsorbing it. The further we move to the right, the more we filter. Transportation rate is kind of talking about filtration. So what this first part of the chart is telling us that the more glucose we put into the blood, the more we are able to reabsorb. It's a 1-to-1 ratio. This first section, we put in 1 molecule of glucose, we reabsorb 1 molecule of glucose to go to the muscle cells of the body to be used for energy or contraction. That is how it's supposed to be. However, once you put too much glucose in the blood, the reabsorption rate reaches its maximum. So we put too much glucose in the blood and we have this plateau where we are no longer reabsorbing all of the glucose we are putting into our blood, which means that we are going to have to get it out of the body in the urine. So even if we add more glucose up here, we are not reabsorbing it. So there are 2 very important points that we can add with this plateau. The first is the T max. That is the transport rate for glucose reabsorption, the maximum transport rate for glucose reabsorption. Then we have renal threshold, which is the plasma concentration at which Tmax occurs. So Tmax is that max rate that we can reabsorb glucose. We hit it once we hit that plateau. And at that same point, we have the renal threshold, which is where Tmax occurs, the max threshold that we can filter glucose, or not filter, reabsorb glucose. So yeah, not a good deal. So we're going to return to this chart in just a second. But before we do, I just want to go over that glucose reabsorption a little more in depth. So again, glucose exists outside of the cell, and the goal is to get it from the lumen or the outside of the body into the body. So the goal is to get glucose into that extracellular fluid. So we see that we can do this with 2 carriers. We have the glucose sodium cotransporter on the luminal side, the glucose sodium cotransporter. So we'll use sodium's concentration gradient from high to low to move glucose against its concentration gradient from low to high to get it into that epithelial cell of the kidney. And then we have another carrier called the GLUT carrier, and it will carry glucose from the cell into the extracellular fluid. So what we see is that these 2 carriers can be saturated. They have a specific binding site for a certain amount of molecules, so they can be saturated, meaning that if we keep adding glucose to those carriers, they will reach a max fill or a max rate that glucose can cross that membrane. So think about it as like an Uber, and we're trying to leave a concert and there's 800,000 people trying to get out. You know, there are only so many spots in Ubers to get people where they need to go. So those Ubers can be saturated or filled to the point where we cannot transport glucose anymore. We cannot reabsorb it into that extracellular fluid. So looking back at this, we see that that reabsorption of glucose is equal to T max. So the max amount of glucose that we can reabsorb is equal to T max because those transport carriers have been saturated. So once you continue or once you reach renal threshold, the more glucose you put into the blood, the more glucose you're going to see in the urine, which is a very bad sign. So we do not see excretion occur. We do not see glucose excretion occur until we hit that renal threshold. So before the renal threshold, we will not see the excretion of urine or of glucose in the urine. It will just be reabsorbed in the body for energy, which is how it is supposed to. But once we hit renal threshold, it will be excreted in the urine, which is not good. So the TA from last semester used an example that kind of made it click for me. So I don't know if y'all ever watched Drake and Josh, but there was this episode where they were working in a sushi factory, and they had this, what do you call it? Like conveyor belt, and sushi was coming out and they had to like take the sushi and pack it. And at first, you know, they were taking it, packing it. They were like, this is easy. We got this. Come on, and like pick it up. And then all of a sudden the conveyor belt picked up. We started adding more sushi and they were like, oh my gosh, we can only do this so fast. And then all of a sudden it picked up so fast, they were throwing sushi all in the room. You know, Josh hopped onto the conveyor belt to try and get it to stop. And overall, they were not able to continue packing up that sushi. That's kind of what occurs here. You know, we can pack glucose and reabsorb it into the body at a certain rate. However, we will hit a point where if we, you know, increase the amount of glucose in our blood at, you know, too quickly in one sitting or whatever, glucose will begin to appear in the urine, which is not supposed to happen. All right, cool. So now we are getting into the actual worksheet. So hopping into that first question, what Dr. Ching is asking us to do is create a model of reabsorption using these three carriers. So we're talking about how we reabsorb molecules of sodium in this example, because we see sodium in all three of them, also glucose. So apical is talking about the lumen, so like the blood, the inside of the blood vessels, inside of the afferent arterial and the capillary beds of the glomeruli. Then we enter through the proximal tubule cells, and then the basolateral is kind of the inside of the body. So apical, again, we're talking about reabsorption, so we're moving in this direction. So we're moving into the body instead of out of the body. Out of the body is secretion, so everything we're doing on this example should be moving in this direction. So what we see is, if you remember back to Unit 1 material, sodium is almost always higher outside the cell and lower inside the cell. So we most always have lower concentrations of sodium inside the cell, higher concentrations outside of the cell. And so the first transporter we're going to look at is the most basic one because it's moving from low to high. And to move from low to high, all we need is a basic channel, a sodium channel, because we're using passive transport. So low to high, passive transport, we just move it through. Sodium is negatively charged, so we need a channel. It's not just going to move without a channel, but it's passive. It's passive movement. So low to high, that's what that concentration gradient. So we just use a channel. So now we need to get that sodium from the cell into the body. And so now we need to move it from low to high, which is against its concentration gradient. So what we're going to use here is the sodium potassium ATPase transporter, which is using active transport. So we're going to break down some ATP, which will allow us to use that energy to move sodium against its concentration gradient into the body. Lastly, we have the sodium glucose symporter. So what we see is that with the sodium glucose symporter, we're going to use the concentration gradient from sodium to get glucose into the cell. So remember, glucose needs to be used by the cell for energy. So whenever we move sodium with its concentration gradient from high to low, the energy created from that, we can also move glucose from low to high. Glucose is going to be kind of higher inside the lumen because we ingest it, it goes into the bloodstream, and then we need to move it into the cells. All right, and again, just refresher, symporter means they're both moving in the same direction. Okay, so there's one more question on this part, and it's asking, how is the reabsorption of water, urea, and chloride linked to sodium reabsorption? And what the answer is here is that sodium is the key to help reabsorb the other molecules. So sodium is how we reabsorb water. When we move sodium into the cell, water will also move into the cell, same as chloride and urea. So sodium is kind of the driving force to help reabsorb the other molecules. All right, so now we're looking at excretion. So we're creating a model of secretion using these 4 transporters. And before we hop in, let's go ahead and review this little note up here. So what we see is that secretion involves the movements of substances in reverse of reabsorption. So now we're moving in this direction. So from the plasma to the lumen. However, the mechanisms are similar. The substances that we're going to secrete are hydrogen, potassium, and organic ions. So let's go ahead and look at this. We have potassium, organic ions, and hydrogen, things that we do not want to reabsorb. We want to get rid of them. So first, simply we have that potassium channel, moving potassium from area of high concentration to low. This should say passive transport. This should say passive transport because we're moving from high to low. So again, a pretty basic one. Then we need to move those organic ions out of the plasma. So what we use is the sodium organics antiporter. So what we see is that we'll use the concentration gradient from sodium moving into the cell to get those organic ions out of the cell, as well as hydrogen. Hydrogen, we also use an antiporter with sodium. Antiporter means opposite direction. So sodium moves in, organic ions and hydrogen ions move out. So pretty important to know because if we keep hydrogen in the plasma, in the body, it's going to affect pH, and we do not want acidic urine. That would be very painful, not good. So we want to get that hydrogen out, and we want to get those organic ions out as well. Lastly, we need to rebalance that potassium and sodium levels. So we'll use the concentration gradient from sodium to get potassium into the cell to keep that sodium-potassium balance. So we'll kind of use the breakdown of ATP for that again. This should not, I just realized there's a mistake here. This should not say can use concentration gradient from sodium because we're moving sodium against it. It should say we'll use the breakdown of ATP to move potassium in. So make sure you know that that ATPase transporter uses the breakdown of ATP to move molecules, not an antiporter or a symporter. Okay, cool. All right, so I'm actually going to end the video here to create a new one because this is pretty in-depth and it takes quite a while. So what we're going to be doing next is our renal math calculations. So everything we've learned so far is really going to help us out with this next portion. But I will see you on just a little bit, or I guess whenever you watch the next video, to go over our renal math calculations. So thank you for watching this video, and stay tuned for part 2.